Greetings from Microlab Northwest. Today we're going to look at Kohler illumination. The microscope is an amazing piece of equipment. But in order to use it correctly, we have to train it. Training the microscope begins with Kohler illumination. In order to get Kohler illumination, we simply have to have the optical planes in the microscope all in the right position so that we have optimal illumination on the particle and the particle is in sharp focus. Manufacturer helps us with part of that. The microscope is designed so that the objectives and the eyepiece are in the correct position in order to give us the ability to focus on a particle on the stage of the microscope. If we take a look at the stage of the microscope, we can use the coarse and fine focus to focus on the particles of interest. Once we've done that, we have focal plane 4, which is the stage of the microscope, in focus at focal plane 6, which is where a reticle would be sitting inside the eyepiece. That would be in focus as well. And finally, the retina, which is focal plane 8. So those focal planes are all set. Because of the design of the microscope, focal plane 5, which is the back focal plane of the objective, is in focus at focal plane 7, which is the eye point of the microscope. Now, the eye point of the microscope, if you take a piece of tissue and you set it on the eyepiece and draw it back slowly, you'll see that image sharpen to a bright point. That point is the eye point. That's where the lens of our eye is located when we're looking through the microscope with everything in focus. So that is already set. What we have to take care of is the focal planes that are below focal plane 4. That includes the substage condenser iris, which is focal plane 3, the field iris, which is focal plane 2, and the lamp, the illumination source, which is focal plane 1. Now, in the base of the microscope, focal plane 1 and focal plane 2 are already in the right position for Kohler illumination. So we don't have to worry about adjusting that. But focal plane 3 is the one that we are critically interested in. That has to be in the right position in order to optimize the image of the object. And let's take a quick look again at the image. If we change the position of our substage condenser, you'll notice that it changes the quality of the image of the particles. We need to optimize that position in order to get a good, clear image of the particle. Now, in order to do that, we're going to use focal plane 2, which is the field iris. That, as you recall, is adjusted here with this little ring. Notice that as we change that, that also affects the image of the particles. Now, we want to adjust this system so that when we change this iris, the only thing that changes is whether or not the leaves of the field iris move into our field of view. We don't appreciably change the appearance of the particles. That's an important aspect of this design. In order to get that condition, here you can see again Rotating that field iris changes the appearance. What we need to do now is we're going to use the substage condenser focus. We're going to bring that up until we can see the leaves of the field iris, and there they are. Now, once we can see the leaves of the field iris, we need to make sure they're centered, and we center that image by using the centering pins located on the carriage of the substage condenser. And if we take a look, these pins can be used to adjust the image of the field iris. We open the field iris to see how it's centered. Need a little more adjustment here, so it's about the same on all sides. And that's pretty close. So at this point, we have Kohler illumination established. Now, this is the starting point for all kinds of analytical procedures. This provides the optimal image of the particles. It provides a separate path for the direct beam, the beam that's carrying the image of the particles, and a path for the diffracted beam, which carries also some important information about the particle. We'll see more about this diffracted beam and why we call it a diffracted beam in another video. But for right now, we'll just consider the fact that we have now separated these two paths through the microscope in a way that we can use analytically. Now, Fritz Zernike won a Nobel Prize in physics for playing around with focal plane 3 and focal plane 5 to change the image that we see in the direct beam. So being able to manipulate these planes independently gives us a tremendous amount of capability with the light microscope. But it all starts with Kohler illumination. So with Kohler illumination, plane 1, plane 3, plane 5, and the eye point, plane 7, are all confocal. Plane 2, the field iris, is in focus around the particle that we're looking at on the stage. That's plane 4. Those are in focus on the reticle that's at the focal point of the eyepiece. That's plane 6. And then finally, in focus on the retina of the eye, plane 8. These 8 planes are critical to optimally using the analytical power of the light microscope. So this is the beginning on Kohler illumination. We'll see some applications as we go further into this. We'll see why Zernike, for instance, might have won that prize in physics for his manipulation of plane 3 and plane 5. And as a matter of fact, we'll actually have an opportunity to play with those planes, and we'll see a very common application of this effect when we use dispersion staining. Dispersion staining basically is a manipulation of plane 3 and plane 5 to give us information about the refractive indices of particles that we might be viewing. So for now, that's enough. We'll see you next time. So long.